Alright, so this is lab 7, and I'm just going to go over some complex power type stuff. So right now this is kind of simulating a perfect waveform. But if we want to say that it has like an offset, so right now this is kind of just simulating the voltage having an offset, like a phase angle difference from the current, and this is not what we want. It's because there is impedance that is delaying the current, or it's either delaying the current or it's holding up the voltage, which, depending on whether you have a capacitance type circuit or an inductance driven circuit, it will govern this phase angle accordingly. And so if you're trying to get them as close as possible, you're actually affecting the power factor, and by setting power factor equal to 1, you are essentially making the voltage and current coinciding with each other. And with a power factor of 0, then that would mean that they would be completely out of sync. So there would be a peak where the trough of voltage would be, or vice versa. And for measuring and like doing AC analysis, you can't assume that the current from here to here is the same, just because this inductor handles current in kind of a odd way. So to be able to do that, you have to take the voltage across this resistor, and since you know the resistance value, then you can just divide by the voltage divided by the resistance and you'll get the current. And then if you want to find the total voltage drop across this load here, then that's when you would just take it from the inductor to the thing, because you want to also get that impedance value of your voltage. Otherwise, it's just the impedance value across a totally resistive circuit is just going to be 0, because there's no impedance associated with that. And so, like we were talking about before, if you are trying to analyze it and measure the values, then you actually have to use the formula where you have to find the period between each waveform. You can either select voltage or current, because they're going to be the same. They're just shifted out by a phase. But the formula that you have to use is you have to find the time difference between voltage and current, and then you multiply that by 360, and then you divide that by the total period of one of these waveforms, and that will get you your theta difference, which you can use. So like I was talking about before, you can use the delta difference here, and this will just calculate the amount that you're differentiating by. And to calculate your power factor, you just take the cosine of the angle difference there. So if we go ahead and look at the results we got here, I'm measuring the delta t by the cursor function. It's on math, but those two lines right there from the yellow to the blue indicate your delta t, and just the total period there. So we end up getting the blue line is the voltage across the resistor, which if you divide it by R is going to be the current. And so as you can see, the current is lagging the voltage because it's occurring after the voltage is read. So as I discussed a little bit earlier, when you're trying to correct a mismatch in phase, you can either add a capacitance or an inductor, and that basically just kind of narrows down to, is your current lagging your voltage, or is it behind it? If it was the case, if it was leading, so if it happened first, then you would want to add inductance to kind of drag it back in to the center line here. And so for this case, there is an inductance value present, so we actually have to add capacitance to bring it back, and this is kind of the result that we got going. As you can see, both of the voltage and current are pretty much in sync now, besides the amplitude, but that doesn't have any factor into the impedance values. That would be more of a resistance type issue. And just to kind of touch up on this again, for the result of the power factor correction, the purpose of this was to not have anything leading or lagging. So neither current or voltage are lagging or leading each other.